this whole crazy subject of dynamical triangulation. Okay, before we start, I have to tell you something slightly important, which is where is the dinner tonight? Okay, so the dinner tonight, you have to bring your name tag one last time, and you have to bring some photo ID. It was like the cookout 2 weeks ago. So the dinner is in a place called the Koenig Alumni Center, and it's on Broadway, basically a 10-minute walk west of here. It's at the corner of Broadway and University. Okay, so it's due west of here. It's the old president's house. Okay, so that's where it is. I will not be walking over there until like 10 minutes to 6, but you can find it on your own. Let's see, what else should I say about the dinner, Dan? Huh? Oh, yeah. So Friday. So TASI ends at 3:15 on Friday, right? Okay, TASI is over. A couple of the locals. Okay, a couple of the locals are going to adjourn to a place called the Rayback Collective. Okay, which is this kind of dystopian place on at 28th and Valmont. It used to be a plumbing supply place, and now what it is a bar with food trucks. Okay, and craft beer. And so you'll have to get over there on your own, and don't bring a name tag. This is absolutely unofficial, but various of us will be over there celebrating, hopefully, another successful TASI checked off against the wall. So that's Friday. But tonight it's official. Bring your name tag, bring photo ID. It's a very pleasant space.
Just one question. So in the calendar, maybe it's my mistake, but in the calendar it's at 8 p.m. But you said
it's at 6. It's at 6.
Wow.
Did the calendar screw it up?
Are you on Eastern time zone?
Oh yeah. Okay. Google is too smart for you.
It's
no,
too
it is
smart.
At 6.
I see. Okay. It's in different time zone.
What's the dress code?
Clothing.
Yeah, it says 6 on my phone.
It's always been 6. Don't do this to me. Take it away.
Okay, thanks. So at the end of last time, I had just introduced superspace, which I'm barely going to use, but it will make one small appearance in today's lecture. This is just so you're familiar with the formalism. We introduced n equals 4 superspace Grassmann coordinates, and then I argued that you can manifest at least half of the supersymmetry if you require that each amplitude include not only a delta function of overall momentum conservation, which is always implied, but also explicitly put a delta function of supermomentum conservation. And being a fermionic delta function, a fermionic delta function, delta of theta is just theta. So that's equivalent to this formula here. And so using this formalism, any superamplitude can be written in the following form. By convention, we put an overall factor here that incorporates or encodes the MHV amplitude. So I put a 1 here. And then higher order terms in the Grassmann-Taylor expansion always come in powers of 4, as I argued last time, due to the R symmetry. And these terms are given various names. If this is called the MHV amplitude, this is next to MHV squared, etc. There's one small exception, which Oliver pointed out. Oops, this is the non-moving. Oh, this is the moving board. For n equals 3, if you're on the branch where the brackets are equal to 0, then the supersymmetrization there was this special case of this amplitude is given by the following expression. Oops, that should be a to 3. So I'll leave it as an exercise. So now it's no longer manifest that this is annihilated by this Q supersymmetry generator. So I'll leave it as an exercise. This is pretty simple. Show this is annihilated by Q, which is the sum I equals 1 to 3 of lambda I alpha eta I A. Okay. And when you do that exercise, you'll need to use some of the special features of three-particle kinematics. Okay, I'm done talking about the supersymmetry now. Are there any questions about this aspect of it? It'll play a small role later on. So what I want to focus most of my lecture on today is momentum twisters, which is a new set of kinematic variables that serve three related purposes. The first purpose is that they trivialize identities, not all identities, but many identities. So you may remember in my last lecture on that blackboard over there that I partially erased, I had written two horrible expressions that were secretly equal to each other. So I'm just going to refer to that formula from last time. I'm just going to refer to it as mess equals mess. And the reason that it's hard to see that mess equals mess is because it doesn't hold for generic spinor helicity variables. It only holds on the locus where total momentum is conserved. Okay? That should always be imposed, but the point is that the spinor helicity variables still satisfy this quadratic constraint. And the identity mess equals mess only holds on the locus where that quadratic constraint is true. So it would be nice to have variables which manifestly, free variables, which manifestly solve this quadratic constraint. And if you had such variables, you might hope that that identity, you could just sit and do it on a piece of paper, check that it's true. And so we'll see why that works. A second benefit of momentum twisters is that they will be variables in which symmetries, old and new, act nicely. So new here is a reference to the fact that in today's lecture I'll explain a hidden symmetry of n equals 4 super-Yang-Mills theory called dual conformal symmetry or dual superconformal symmetry. That in particular includes special conformal transformations in momentum space. Okay, so this is a rather non-obvious symmetry that happens to be true for planar n equals 4 Yang-Mills theory. And that will allow us, by the end of my lecture, to finally phrase the question of identifying the kinematic space, the kinematic domain, for n equals 4 Yang-Mills theory, which has dimension, well, I'll continue on the next slide. It has dimension 3n minus 15, that being 3n minus 10 that Pedro explained, that you have for n particles scattering in 4 dimensions. Then we have minus 5, and you can understand this minus 5. Let me write it as minus 1 minus 4. The minus 1 comes from scale invariance. There's no scale in n equals 4 super Yang-Mills theory, and an n particle amplitude, as I recalled last time, has dimension of energy to the power n minus 4. So if you were to simultaneously rescale all of the momentum variables, every amplitude has to scale homogeneously. Okay, so that's not an independent, there's no possible, there are no masses, there's no non-trivial, so one variable out of these 3n minus 10 just corresponds to an overall scaling of all the momenta, and that acts sort of trivially on amplitudes. Amplitudes are covariant under it. And then the minus 4 is due to, and this we'll see in today's lecture, special conformal transformations in momentum space. So that's the outline for today's lecture. Okay, so what we want to do then is we want to trivialize this condition. And one way we can do it is as follows. Let's imagine this is in Minkowski space. We just put our vectors back to back. Now, as I've already discussed, in the planar theory, there's a natural cyclic ordering when we talk about ordered subamplitudes. So there's a natural ordering of the momenta, P1, P2, P3, etc. And if we simply place them back to back, yes?
Being a little pedantic, do you want the delta function and the equal 0?
No. Thank you, Oliver. Okay. Yeah. Okay. Yeah. Good. If we put them back to back, then this condition says that they form a closed polygon. A closed polygon with light-like edges. Okay, so we can trivialize this by introducing new variables corresponding to the positions of the vertices. So what we do is let pi equal xi minus xi plus 1. So that, for example, this vertex here is x1, the location of this vertex is x2, and this vertex is x3, etc. And this vertex is xn. Now the use of x's for these variables can sometimes be slightly confusing, because don't fall into the trap of thinking that these are position space variables. These are most definitely momentum. They're more closely related to momentum space than to position space. And these are sometimes called dual momenta or region momenta. So I'll just refer to them more loosely as dual variables. And in superspace, we can introduce a corresponding superspace variables like this. Now, by the way, just for efficiency here, I'm always going to, or I'm often going to neglect indices. But if you want to be an absolute stickler, remember that anything that's a 4 vector carries a left and right-handed Lorentz index, and the indices here, oh, and there should be an I there. If you want all the indices written out in gory detail, you need to do this. Okay, but often I'll suppress indices except when they're absolutely necessary. Okay, so it's clear that now if you take the cyclic sum of these pi, it's going to add up to 0 manifestly. And remarkably, in these variables, amplitudes in planar super Yang-Mills theory exhibit what's called dual superconformal. I'll only discuss the part, not the super part, symmetry. Okay, it's manifest. Let's take a look. It's manifest that translations in X space are a symmetry, because a translation in X space has no effect on P whatsoever. Similarly, it should be clear that a rotation in x space just corresponds to a rotation of momenta, so that's obviously a symmetry of amplitudes. Scale invariance in momentum space I already discussed. The only non-trivial thing for us to discuss here is this special conformal transformations in momentum space. Now you know that you can get a special conformal transformation by doing an inversion and then a translation and then an inversion. So the only thing I'm going to explain to you is how this discrete inversion operator acts. So I'll write it here and then I'll move the board up. Inversion normally takes a 4-vector to that 4-vector divided by its length squared. And if you work out what that is at the level of when we're thinking about x, remember how we're thinking about momenta as a 2x2 matrix when you multiply them with the Pauli matrices. So this operation is equivalent to inverting that 2x2 matrix. And then I'll just write here how I acts on the other variables. I think I've been a little unclear about alpha or A indices. Okay, so the inversion acts on x in that way. It acts on theta in this way. You can define it to act on the lambda and lambda tilde variables. So let me circle these. Okay, let me move this board up. And then the last thing I owe you is a formula telling you how it acts on lambda tilde. And this one is interestingly non-trivial. Notice in particular that in all of these formulas I never wrote an I subscript because the inversion acts independently for each separate particle. That's no longer true for the lambda tilde. Here, in order to know how to act with the inversion operator on lambda tilde, it involves the next door neighbor particle. And the reason for that is, and I'll assign this as an exercise, check that the relation is preserved. So remember that the lambda and lambda tilde variables, by definition, they're such that lambda times lambda tilde is p. But now we've introduced these dual variables where pi is xi minus xi plus 1. So what you should check is that if you take this boxed equation and you apply this inversion on lambda and lambda tilde and xi plus 1, using the boxed formulas, you should find that this relation is preserved.
So was it your choice that lambda behaves more nicely
Yeah,
than the tilde?
absolutely. So there is some degree of choice here. That's just some common choice that's in the literature. I'm just getting new chalk here. Right. Okay. Oops. Let me continue here. I still have a little more room. Yes?
Are these x variables are still on shell?
The question is whether these x variables are still on shell. Absolutely. So I'll put that as an aside. Note, xi minus xi plus 1 must be a null vector for each I. Okay, that will play a very important role in just a moment. But that's the statement here, that every edge of this polygon is a null. Okay. And also that's implied here in this formula, because the left-hand side, I mean, that's why you asked the question, I guess, but the fact that xi minus xi plus 1 can be written as a product of these two can only be done if it's null. Okay, so now here's the claim. We'll see that a collection of null separated x's is in one-to-one correspondence with n ordered points I'll call capital Z in projective space, P3. Okay, so that's the statement, and now let me prove it. Okay, first we'll go this way. I'll prove that if you give me a collection of null separated xi's, I can use them to construct n points in P3. And the way I do it is contract both sides of lambda tilde equals xi minus xi plus 1 with lambda I. And when I use that word contract, let me be precise about what I mean. Here are the indices alpha alpha dot, alpha alpha dot, alpha alpha dot. I mean multiply by epsilon alpha beta lambda I beta. Remember that these indices alpha and beta, they're always contracted with the epsilon symbol. So when I say contract, that's what I mean. Well, what happens is the left-hand side is going to give 0 because we're going to have lambda I and lambda I contracted with an epsilon symbol. So we get 0 equals okay. Now here, just to be absolutely here again, I'm not showing, I'm saving time and space by not unnecessarily showing indices, right? This has a dotted and an undotted index. The undotted index is free. The dotted index is free. The undotted index is contracted with the undotted index of that with an epsilon symbol. But I just don't want to write it all out. Okay, so there's a unique way to take this formula and put all the indices back. Okay, so that's all you need to know. So because these two things are equal to each other, let's define mu, let's define this thing to be mu I alpha dot. The fact that these two things are equal to each other signals that maybe there's something sufficiently significant about the fact and we should give it its own name. Okay, then note that under a little group transformation, remember that under a little group transformation, lambda and lambda tilde scale oppositely. But mu scales the same as lambda. That's clear from this formula because x doesn't scale. X is related to momentum. So therefore, if we define zi to be equal to lambda I1, lambda I2, mu I1 dot, I really apologize. There's no way to make this, so I have to say this. This is not an I superscript. This is a 1 dot, okay? Because the upper index of mu is a dotted index. Sorry, there's nothing I can do about it. And then the next index is mu I2 dot.
You could give the one little, like, you know, certain.
I can't do it on the blackboard. Okay, I'll try. Okay. Anyway, the point is this is now a 4-component object. This is a 4-component object, and everything in all of our formalism has to be invariant, or at least covariant, under scaling all 4 of these entries simultaneously by the same factor w. So this is a homogeneous coordinate on P3. And I'm using complex projective space because, as I said, you know, until further notice, it's always beneficial to allow yourselves to contemplate the entire complex domain for your kinematic variables. I'll say more about that later, but for now, we're pretending these are arbitrary complex numbers. I mean, of course, it is an interesting question to ask for what values of these correspond to real momenta in Minkowski space. But for a moment, let's delay that question. Okay, are there any questions about that? So that completes half of the proof. I showed you that if you give me a collection of null-separated x's, I can use that to define endpoints in P3. Now let's go the other way. Oh. Let me just add one more comment. It's actually a supersymmetric P3/4 because we can define the analog for the fermionic for the Grassmann coordinates. Okay, so there's an analogous property that holds for the Grassmann coordinates, so you actually get P3/4. But anyway, now I want to do the proof the other way. Okay, so you give me endpoints Z1, Z2, up to Zn in P3. Okay. I define xi alpha alpha dot to be the solution to the linear equations well, yeah, mu I alpha dot equals lambda I xi alpha dot. And okay, now where did this second equation come from? Well, it came from right here. I mean, we're assuming that you simultaneously have a collection of these that satisfy these equations for all values of the index I. So if I take this equation and just replace I goes to I minus 1, I get this equation that's written here. So this is a total of 4 equations, right? There are 2 equations here because alpha dot takes 2 values. There are 2 equations here, alpha dot takes 2 values. They're linear equations, so generically, you know, unless you're at some special kinematic point, generically, you'll be able to solve for these 4 components of xi alpha alpha dot. Now it remains to check one thing. So that gives us a collection of x's. We have to check that they're null separated. I'll lower an index here using okay, that's a formula we had some time ago. And now the point is, this proves that this 2 by 2 matrix, has determinant 0, right? Because we found it has a null space. And because that 2 by 2 matrix has determinant 0, that tells us that xi minus xi plus 1 is null. So, I could not have planned this better. Oh. We have this picture in dual momentum space, and then we have a corresponding picture in P3, where we have endpoints etc. Now, corresponding to each line, so between any, now it's very important that the points have a cyclic order, as I've discussed. What that means is that you can, for every pair of points, like Z1, Z2, you can draw the line through Z1 and Z2. Then you can draw the line between Z2 and Z3, the line between Z3 and Z4, etc. And as we've seen through these equations, every point here corresponds to one of these lines. Every vertex here corresponds to one of these lines. Etc. And so correspondingly, you can sort of think of these edges as corresponding to these vertices. Okay. This is essentially Penrose's twister theory, which says that null rays in Minkowski spacetime are in one-to-one correspondence with points in P3. The only thing different here is we're not applying this to spatial Minkowski space, but we're applying this to momentum. This is momentum space. So that's why these things are called momentum twisters. They were first introduced by Hodges, but the underlying theory is essentially that of Penrose's twister theory. So that's why these are called momentum twisters. But the point is that finally, these variables give us a completely free, completely unconstrained parameterization of the kinematic space. Okay, so I'll summarize that here. The Zi are unconstrained. If you give me a collection of Zi, they determine a collection of 4 momenta such that pi squared equals 0 and sum of pi equals 0. With one important caveat. So let's do Pedro's dimension counting, right? This is a non-trivial submanifold of C4n. Okay, what is its dimension? As a submanifold of C4n, this has dimension 3n minus 4. Because you have n null momenta. A single null momenta has 3 independent degrees of freedom. Then there's overall momentum conservation that imposes 4 extra conditions. So I only have 3n minus 4 here because only the translation symmetry is made manifest yet. Laurent symmetry has not yet been imposed. So we're still waiting for an extra minus 6 to come in a few minutes, but for the moment we have 3n minus 4. On the other hand, here we have a collection of n points in P3. So the dimension of this space is just 3n. Because, well, P3 is 3-dimensional. You have n points, that's 3n dimensions. So there's a discrepancy here by 4. So something was snuck under the rug. And what it is pretty simple to understand. If you want to get the dimensions to work out, notice that there's nothing that determines the choice of origin in X space, right? If you give me a collection of P's, the formula is erased now, but it's basically, if you give me a collection of P's, there's no canonical choice for an origin in X space. So if you want to make the dimensions here match, you should do union choice of origin in X space. Now, so we've introduced an additional redundancy now that we better get rid of. We know that amplitudes can't possibly depend on the choice of origin in X space because that's an auxiliary thing that we introduced. So we went from 3n minus 4 back up to 3n. But don't worry, we're gonna get rid of that minus 4 in just a second. Just remember it in the back of your mind. I want to do an aside now because I promised that one of the killer apps for this momentum twister construction would be trivializing identities.
let's define the following objects. First, we define the 4 bracket, which means the determinant of Zi, Zj, Zk, Zl. So each of these Z's, remember, is a 4-component object. Okay? And there's one for each particle. So I define the 4 bracket to be the determinant of the 4 columns given by the 4 corresponding Z's. And then I define a 5 bracket, which is the following. Down here, it's just the product of all cyclic sets of 4 out of 5. Okay, so far it's just a definition. This is a 4-dimensional delta function because that eta carries a free Grassmann index A. Then you can check. So I'll put this as an exercise. And this time it's actually doable. 1, 2, 3, 4, 5 minus 2, 3, 4, 5, 6 plus 3, 4, 5, 6, 1 minus 4, 5, 6, 1, 2. Sorry, yeah, I said it correctly and wrote it wrong. 5, 6, 1, 2 plus 5, 6, 1, 2, 3 minus 6, 1, 2, 3. Too many indices there. Equals 0. Okay, this is an exercise you actually can do with pen and paper. And I claim, so notice that this is a supersymmetric identity because it involves the Grassmann variables. I claim that this implies, so one of the components of this thing is the horrible identity I had on the blackboard last time, mess equals mess. Now, in that example, I had 2 terms equals 3 terms because I happen to be looking at a component where one of these 6 terms is 0. But,
Sorry, Marco.
yes?
The last 2 have only 4.
Yeah, sorry, I screwed it up. I was getting confused with the 4 bracket. Yeah, thank you. It's the alternating sum of all the cyclic permutations of this thing. Okay, so, I mean, if you're too lazy to do this by hand, you can just plug this in Mathematica and literally just type factor. You'll get this will give you some whole long mess. Type factor. It will all factor it together and it will give you 0. In contrast, if you take the expression I wrote on the board last time, the huge mess, and type factor in Mathematica, nothing's going to happen because it doesn't know that the lambda variables are constrained to satisfy that quadratic constraint. Okay, so mission 1 accomplished. Remember, I had an outline for the lecture. Okay. Okay. Are there any questions about this? Now,
are you making some intersections between hypersurfaces testally or secretly so that you get dimension 3n minus 4?
well, in a sense, I'm taking the intersection of these hypersurfaces. Nothing more sophisticated than that. I mean, yes, this is, this is not a linear subspace of C3n. It's a curvy subspace, but it has this component has dimension 3n minus 4. Any other questions? Okay, so item number 2 on my wish list was to that the variables should be such that they're useful for such that the symmetries act nicely in these variables. We have 3n dimensional space. Okay, and we know, as I already argued, we're supposed to get down to 3n minus 15. So what symmetries have we not yet imposed? Okay, this component of our, we know that amplitudes absolutely cannot depend, I said this already, so I'm giving the same speech again. Amplitudes cannot depend on this choice of the origin in X space. So this we just have to throw away. So we need to take this, but it's definitely there. It's built in that, so different choices of z's do correspond to different choices of origin in X space, so we need to get rid of that. So we'll need somehow to implement a symmetry that cuts out 4 dimensions. Then, of course, there's Poincaré. Now, this acts pretty nicely at the level of momentum twisters, because remember that the first 2 components of a momentum twister are a doublet under the left SU2, and the next 2 components are a doublet under the right SU2 of the Poincaré group. So that will turn out to be easy to implement. Scaling I've already discussed. Now I claimed, without proof, I claimed that this inversion transformation is a symmetry of scattering amplitudes, and you can use that inversion in the usual way, inversion, translation, inversion, to write down 4 special conformal transformations. So altogether, we need to somehow find a 15-dimensional symmetry group acting on the z's. So by the way, I mean, it's clear, I'm not rigorously writing down what all the generators are. I'm not deriving their commutation relations. Of course you can do that. I'm just saying let's count how many there are, and I'm going to tell you what the answer is. Okay, because the answer is simple and beautiful and obvious. Yes, in the back.
Conformal symmetry is a non-perturbative symmetry of this theory. Is that true for a dual?
The question was, conformal symmetry is a non-perturbative symmetry, and the question was, is dual conformal symmetry also? And I think the answer is yes, because you can see dual conformal symmetry in the ADS CFT side. You can see it as a kind of a T-duality transformation in the dual superstring action. Okay, so the answer is that the kinematic, imagine you put all n of your z's into a 4 by n matrix. So the claim is that this 15-dimensional symmetry group corresponds to left multiplication on this matrix by SL4. The dimension of SL4 is 15, so at least the dimension works out. But I assure you this is correct. So the claim is the kinematic space for n particle scattering in planar, we need planar to get the color ordering, n equals 4, super Yang-Mills theory is n points in P3 mod SL4. And the dimension of this space is 3n minus 15. So this finishes mission 2 and mission 3. Okay. Yes. Yeah, it's not so hard to work out. Like, let's say you wanted to look. The question was, is there a nice way to see what the generators correspond to? So yeah, let's discuss a few of them. Here I gave the answer. If you do a rotation on the first two components of Z, that's a left-handed Poincaré. If you do an SU2 translation on the right, transformation on the last two components, to see what translation symmetry in X space does. Well, I've deleted all the formulas now, but if you go back to all those formulas relating the lambdas, the x's, and the mu's, if you do a translation on the x's, like xi goes to xi plus constant, you'll see it does a very simple, it's a block diagonal transformation that shifts, I think it shifts lambda I by some multiple of mu I, or something really simple. And the scaling symmetry you can work out similarly from those formulas. The only one that's maybe slightly non-trivial is to work out the special conformal symmetry, but yeah. Okay, now the mathematics of this space is very poorly understood, and it's a subject of active research. But it's a very close analog of a space that many of you may have seen before if you've studied string theory. Yeah?
This is really a dumb question, but it looks like what you're getting is like intersection points of n lines. Could I understand that somehow you're looking at some Grassmannian?
Yeah. Oh, yeah. So absolutely. So yeah, before I get, okay, so you can think about this. This is, okay, since you sound mathematical, I get to throw it back at you with words like birational isomorphism. So this space is birationally isomorphic, and I'll tell you what that means. To a Grassmannian 4, n mod C star n minus 1. So let me explain why this is. Okay. If you just imagined the set of 4 by n matrices modulo GL4, that would define a point in the Grassmannian, GR4, n. That's not quite what we have here, because in addition, we're supposed to take equivalence classes of points in that Grassmannian under arbitrary rescalings of the columns individually, because each column is a point in P3. It's a homogeneous coordinate. So we should mod out by C star to the n, except that it's not quite n, because an overall rescaling of all columns simultaneously pulls out and turns this SL4 into GL4. So another way to think about this space is the quotient of the Grassmannian 4, n mod C star to the n minus 1. And the word birational isomorphism just means that these are isomorphic for generic points. But on boundaries of this, if you think about this as a moduli space, which is where that comment is headed, on boundary components of that moduli space, this space can have segments that are blown up compared to that space by some rational map. So in string theory, you are familiar with the string moduli space, tree level, of n marked points on a sphere, or n points in P1 mod SL2. So this space that we encounter is an exact analog of what you may already be familiar with from string theory, except it's somewhat more mathematically sophisticated and quite a bit more intricate. Okay, are there any questions about that? So I now actually want to delve into, because I don't understand much about that space, I want to review some things about this space. And I can still claim that I'm lecturing on scattering amplitudes, because those are relevant to scattering amplitudes. And at the end of my final lecture tomorrow, we'll see an application of this to phi cube theory. But I think I'm done for the moment with n equals 4 super Yang-Mills theory. So if there are any lingering questions about that, this is a good time. Okay.
I have a lingering.
Yes.
So I know we talked about how the 3-particle scattering is special, but it
Yes.
looks like you have to go at least to 6-particle scattering before this is a meaningful construction.
That's right. So the question was, this dimension is 0 or even negative, which means non-existent, unless n is equal to 6. And the way to think about that is, remember that you can use little groups, as I explained in my first lecture, you can use little group scaling to determine the overall bracket dependent factors in any amplitude, just by knowing which particles are in that amplitude. Then you can have an arbitrary function of, in a general field theory, arbitrary function of Mandelstam invariance. In n equals 4, you're more restricted. You can only have an arbitrary function of dual conformal invariant cross ratios. So exactly the analogous kind of thing you may be familiar with from conformal field theory, cross ratios that you can build that are invariant under this dual conformal symmetry. And there are only 3n minus 15 of those. So the statement is that 3, 4, and 5 particle amplitudes are completely determined in n equals 4 Yang-Mills theory, up to an overall constant that we call the G Yang-Mills, or the 't Hooft constant, since we're in the planar theory. The 3, 4, and 5 particle amplitudes are completely determined. There's no room for any functional dependence on conformal cross ratios because there are none. And only starting at 6 points can your amplitudes be interesting, non-trivial functions of these dual conformal cross ratios. Yes?
So, for example, you said like 3, 4, and 5 point amplitudes are completely determined.
Yes.
Do they factor into one another?
Absolutely. Well, yes, absolutely. They have to. Yeah. Now I'm hiding something under the rug here, which is that when you work in perturbation theory, these things are infrared finite, so you have to introduce a regulator, and the regulator will typically break conformal invariance. There do exist regulators that preserve dual conformal invariance, which is really neat. But there's a whole story there, and a lot of it is pretty well understood, but it's not what I intend to lecture on now. But if anybody wants to ask, this is the opportunity. Okay. Yeah. Yes.
How does ordinary conformal invariance act?
Oh, excellent question. Yeah, it's rather complicated. The question is, how does ordinary conformal invariance act on momentum twisters? Yeah, so that's an interesting story, just to see the ordinary conformal invariance. That has all been worked out, but I'm not prepared to say anything intelligent about it right now. So let me see what I can say. Well, one element of it we've seen, the scaling. The Poincaré is the same. The only missing generator is the ordinary special conformal symmetry. But I think that's already broken. Yeah, it's this crazy. I mentioned that in my first lecture. It's this operator that's second. It's a second order differential operator. So it's rather non-trivial. It's not simply realized. Let me say it that way. So these momentum twisters have the advantage of manifesting the dual conformal symmetry, but not the ordinary conformal symmetry. Okay, any other questions? Okay, good. So, one of the cool things about this moduli space is that on the boundaries of the moduli space, as two of the marked points start to coincide, the space factorizes into products of smaller spaces of the same type. And that's necessary for the consistency of string theory, that if you have a sphere and you have 10 points on the sphere, and let's say 5 of them are grouped together here, and they become very far apart from 5 of them that are grouped here, you can use an SL2 transformation to push them very far apart, and think about it as 2 copies of a moduli space of 6 marked points, because you have the 5 here plus the additional point where the tube is attached. This space, by contrast, has much more fascinating boundary structure. It does not, in general, factorize into products of 2 copies of this thing, but into products of many copies of this thing. But as I said, because we don't understand very much about this, I want to say some interesting things about this that are also relevant to that case. Okay. Okay. So one thing that so let's call this G2n mod C star to the n minus 1. One thing that G2n and G4n mod C star to the n minus 1 have in common, indeed this is true for arbitrary k, you could put any integer k here, is that they are examples of cluster Poisson varieties. What that means, for the purpose of my lecture, is that they have a natural Poisson structure and preferred sets of coordinates that are log canonical with respect, like I'm using that phrase in the same way that you talk about canonical coordinates, like on a phase space, p comma q Poisson bracket equals 1, that are log canonical with respect to the Poisson bracket. And the word cluster means that those coordinates are related to an object called cluster algebras. So in the last 10 minutes of this lecture, I'm going to give a lightning review of cluster algebras. at least those aspects which are relevant for scattering amplitudes in Yang-Mills theory.
Sorry if I missed you saying this,
Yeah.
Mark. What is log canonical?
Oh. Okay. So I'm going to introduce these coordinates, and then in the next lecture we'll see what this has to do with the moduli space of endpoints on a sphere. The simplest cluster algebra, non-trivial, is called A2 for a reason that you'll see in just a second, and it's based on the following observation. Let's consider the recursion xi plus 1 is equal to 1 plus xi over xi minus 1. So this is similar in flavor to the Fibonacci sequence in the sense that if you want to know a given x, you need to know the two previous x's. So in other words, to seed the series, we need to start with two variables that we call x1, x2, and then x3 is determined by the recursion to be this, and then x4 is further determined to be this. Okay, and there's a danger this is going to get arbitrarily complicated very quickly, and indeed, just like string theory goes bad if you try to break any rule in even the most minor way. If you change any detail here in even the most minor way, this is all going to just collapse and nothing nice will happen. But for precisely this choice, if you plug this in, you'll find, maybe I should do it because you won't believe me otherwise. After combining the numerator here, factors into that. So altogether, x5 is equal to 1 plus x1 over x2. And in a similar miracle, x6 turns out to be x1, and x7 turns out to be x2, etc. So this sequence, it's totally not obvious from this formula, but this sequence is periodic and it has period 5. And an important thing that happens in cluster algebras is the so-called Laurent phenomenon, which is that the denominator of any one of these variables, these are called cluster variables, and the Laurent phenomenon, which has been proven in great generality, is that the denominator is always a monomial. And as we see here, that relied on seemingly fantastic cancellation of various factors. Anyway. Cluster algebras can be associated to quivers where, for my purposes, a quiver is a graph with some number of nodes and directed arrows between them. Except that I'm going to allow in principle, more than one arrow from one node to a next. I'm going to let Bij equal the number of arrows from node I to j minus the number of arrows from j to I. And I'm only going to consider graphs where one of these terms is non-zero. So what that means is I do not allow this. If I ever had a graph like that with two nodes connected by arrows in the opposite direction, I would first cancel them. Okay. And then we label each node with a variable. For example, so now I'm going to do the simplest case. And now you can start to see why this is called the A2 cluster algebra, because this resembles the Dinkin diagram of A2. So this would have the matrix, oops. Well, note is too strong a word. Claim. Okay, in the cases that we're interested in, this graph actually encodes the structure of what I said is the canonical Poisson bracket. And I think I'm going to have to stop here because next I want to redo this example in a somewhat more general setting, and then the rest of my lecture next time will be explaining what on earth any of this has to do with the moduli space of endpoints on a sphere, and then discuss very briefly what the corresponding generalization to n equals 4 would be. But there is a question in the back.
So if I just give you the quiver or the d-matrix or anything on that board,
Yeah.
how do you reconstruct the recursion relation?
Yeah, that will become, I'll write the formula next time. The question was, if I give you that combinatorial data, like write the B matrix or equivalently draw the graph, how would you know what this formula is? And I'll write it next time. Yes?
Is that similarity between the kinematic spaces in this context and Trivialize
Yeah.
continue to hold for loops where you have?
Oh, absolutely. Absolutely. So this thank you. The statement, the question was whether the similarity that I've mentioned between the this kinematic space and the one in string theory continues to hold at loop level. And yeah, so it's an excellent question because the parallel ends on the string theory side, because this is of course the moduli space for string theory at tree level. But in n equals 4 Yang-Mills theory, this is the kinematic domain non-perturbatively. Okay, so it does diverge in that sense, but this is the non-perturbative kinematic domain in n equals 4 Yang-Mills theory, as far as we know, unless there's some hidden symmetry that hasn't yet been discovered. Okay, any other questions?
Let's thank you.
Okay.